Last time we wrote the propagator, this propagator here in the frequency domain. We wrote it like this. As you can see, this is the seemingly complicated expression where the partition function is written here. We expanded the exponential first order in lambda. So here you can see that we have lambda for the partition function, but also for the propagator. So here we have lambda as well. This is z, but in the expression for the propagator we have 1 over z. And 1 over z, we saw it last time, can be expanded like this. So we have 1 over z0, where z0 is simply this integral here, where we have just 1 inside the integral and then this exponential. And then, as you can see, this is just a bunch of Gaussian integrals. So it contains several Gaussian integrals. We also defined b. b is basically this part of the integral. It's this, and then we have this part as well. And then you have to divide by z0. So in principle, we are interested in b over z0. Let me write it for the sake of convenience. So here we have the integral d phi hat. In particular, this d phi hat, as I said last time, it is made up of several differentials, like the differential of mode phi hat sub minus n, differential of mode phi hat sub minus n plus 1, all the way up to, in principle, infinity. So you have a bunch of these differentials. Now let me cancel it. It's not really important. Here, then I have e to the minus 1/2 summation over j mod phi hat sub j squared k j squared plus m squared. Then we have summation over n. Now let me write it like this: summation over n1 and n2 mod phi hat n1 squared mod phi hat n2 squared minus summation over n mod phi hat sub n to the 4th. And then we divide by z0. z0 is simply integral d phi hat e to the minus 1/2 summation over j mod phi hat j squared kj squared plus m squared. Now, the integration over all the Gaussian integrals, just to let you know, but it is quite intuitive. So when you integrate, for example, over d mod phi hat 1, you have to integrate from 0 to infinity. This is a mode, a magnitude, so it stands to reason that you start at 0 and then you go all the way up to infinity. And all the Gaussian integrals are normalized because, as you can see, you also have a Gaussian integrals here in the denominator. So this is actually simpler than it seems, because it seems complicated, but it is not as complicated as it seems. So we can evaluate b over z0 by knowing how to calculate Gaussian integrals, and I will not get into the details of how to compute Gaussian integrals. They are quite straightforward if you know just multivariable calculus. In particular, let's start by assuming that, for example, we are integrating these two terms first, assuming that n1 is not equal to n2. Well, if n1 is equal to n2, basically we can see easily that we will get a 0. This minus this will give you 0 when n1 is equal to n2. But let's write it down. So if n1 is not equal to n2, what we get is the following summation. We have a summation over n1 not equal to n2, and basically it is just this summation here that we can put outside of the integral, then we integrate such variables. First, we are integrating over those variables that, we are assuming that n1 is not equal to n2, so we integrate this phi hat sub n1 squared, and then we integrate this phi hat sub n2 squared, and they are independent Gaussian integrals that will get normalized thanks to the presence of this z0 in the denominator. So it is quite simple. It is less complicated than it seems. And here, what we get is basically the variance of the first calculation, which is a 1 over k n1 squared plus m squared. And then you get the variance from the second integral, k sub n2 squared plus m squared, like this, right? And then, in principle, you have to calculate the same thing, assuming that n1 is equal to n2, and of course, you also get a similar contribution here. So the integral of something like mod phi hat to the fourth, with all the other, let's say, parts, it will give you 3, and then, of course, you will have 1 minus 1, and this will be 0. This first one comes from this integration, when n1 is equal to n2, and this second one comes from the integration of this other term. And then here you have the variance squared. In particular, you have to sum over n the variances of this kind. 1 over kn squared plus m squared squared. So this is the variance. Then you have to square it to get sigma to the fourth, the standard deviation to the fourth, whereas the variance is just sigma squared, or the standard deviation to the second power. Now, I'm just leaving this term for the sake of convenience so that you will understand maybe a little bit better. But of course, you can get rid of this because this is 0. But we will keep it. We will keep it there. Then, remember that, so we have calculated b divided by z0, right? And that appears in the expression of 1 over z, because we have exactly this. So basically what we want to do is we want to rewrite this expression in the following way. So here we can put z0, and then after we calculate the integral, we can multiply everything by 1 plus 1 over 8 lambda b divided by z0, like this. We have already evaluated b over z0, so we know what to put here, but we have to evaluate this other part, this one here. Right? So this is what we want to do at the moment. And if you think about it, it is just, it is very similar to what we did for b over z0. In this case, there are some differences, because you have this extra part, phi hat sub h squared, that multiplies everything, but in principle you do exactly the same thing. And let me do it below. So we have to do it, so let's do it. Average of mod phi hat sub h squared, this is approximately equal, so I'm putting this approximation symbol because remember that we are going to truncate our expansion to order lambda. And here we have the first term is 1 over k sub h squared plus m squared. And this is just the free propagator, if you think about it. So what you're going to get, that term arises when you multiply this term by 1, and then you do the integration. That's very simple, right? So here you have a phi hat sub h squared, and that will give you the variance of the Gaussian distribution. So in this case, you just have this term, very simple. And then you have some more complicated terms. So one term is minus lambda over 8, and then you have to sum over n1 and n2 such that n1 is not equal to n2 and n1 is not equal to h. and also n2 not equal to h. So what I'm going to write here will be the result of the integral, in particular, where is it? This one here. So if you rewrite this term as summation over n1 and n2 mod phi hat sub n1 squared mod phi hat sub n2 squared, when you multiply this by mod phi hat sub h squared, of course, the result of the integration depends on whether n1 is equal to n2 or n2 is equal to h, and so on and so forth. In the first term that I'm calculating, I'm assuming that n1 is not equal to n2, and both of them are not equal to h. Okay? So what we get is this term, so we get a minus lambda over 8. The factor lambda over 8 comes from this lambda over 4 factorial times 3. And here, when you do the integral, you will get something very simple, 1 over k n1 squared plus m squared times 1 over k n2 squared plus m squared times 1 over kh squared plus m squared. And then you also get another contribution of the following kind. You have minus lambda over 8. Then you get a factor of 3. And this factor of 3 comes from considering n1 not equal to n2, but n1 is equal to h. And since there is symmetry with respect to n1 and n2, here we can multiply this by 2. So this factor of 2 covers also the possibility that, so I don't have to write the same summation, n1 not equal to n2, and n2 equal to h. So this summation here will give exactly the same result as this. Therefore, that's why I'm putting the factor of 2 here. So you just have to think about it. It is less complicated than it seems. And then here I have the factor of 3, because when n1 is equal to h, I get a factor phi hat sub n1 to the fourth, if you think about it. So when you integrate that, you get a factor of 3 related to the kurtosis of the Gaussian distribution, but never mind, if you don't know the word kurtosis, it's not a problem, because we don't need to know that in order to do the calculations. Here we have 1 over k sub n2 squared plus m squared, and then we have 1 over kh squared plus m squared, and this is squared. Then, what else do we have? We have plus, and in particular, now I'm going to put a minus here, so we have minus lambda over 8, and then I have 15, and this 15 comes from the integration of phi to the power 6. So phi hat mod phi hat sub h to the power 6. In particular, here I'm considering the possibility that n1 is equal to n2, which is equal to h, right? So n1 equal to n2 equal to h. And in particular, where is it? So wait a second. I'm assuming that n1 is equal to n2, which is equal to h, and therefore you will get that factor of 15 times sigma to the 6 that I have to write. And then that will also be cancelled by this other part when n is equal to h, and you multiply this, that by this, and therefore it's easy to understand that you will get a zero contribution, but I'm just writing for the sake of convenience, just to remind how these terms arise. So this is multiplied by 1 minus 1. Remember that. I mean, this is 0, of course, but I'm just writing them down in order to maybe improve the understanding of these calculations, hopefully. Here you have 1 over kh squared plus m squared raised to the third power. So this is 6 sigma to the 6. Or if you want, sigma squared, which is this one, to the power 3, the variance to the third power is the standard deviation to the sixth power. And then you have just one final term, minus lambda over 8, and then here you have to multiply this by 3, and this factor of 3 is related to an integral of phi to the fourth, just like the others. I mean, just like this one here. But in this case, we are summing over n1 equal to n2. So I can write it like this. I can put n here. We also have the condition n not equal to h. I will tell you a little bit more about this summation in a moment, but first let me finish writing the expression. We have 1 over kn squared plus m squared to the second power, and then we have 1 over kh squared plus m squared, and this is multiplied by 1 minus 1. So this is 0, and of course this term can be neglected. It will simply be 0. Simple as that. But how does this term arise? This term arises when you consider n1 equal to n2. So here you have something proportional to phi to the fourth, just like in here, and we are assuming that those terms are not equal to h. So you can compute the integrals, but of course you can understand easily that that will give you 0 contribution, because this contribution will be cancelled by this. So I have written down the expression in full form, but you have to be aware, of course, that this term here will simply be 0, then you have this term that's 0, and so this simplifies quite a lot, right? Remember that this expression here, probably now I can thicken my pen so that you can see the whiteboard more clearly. So here I am going to use 5 as the thickness, and this is multiplied by what? Well, remember that we have to multiply the result by this expression here, right? We have already calculated that, and therefore we have 1 plus lambda divided by 8, and then we have to multiply this by this lambda over 8 by this. It's the expression that we have already calculated. Now, probably now I can avoid writing down this term, so I'm just going to write this, and here we have to sum over n1 not equal to n2, and then I have 1 over k n1 squared plus m squared multiplied by 1 over k n2 squared plus m squared, and then you have higher order terms. Now when we do the multiplication between this parenthesis here and this parenthesis here, we are going to neglect second order terms, because you can see that we have this lambda, and when this lambda multiplies this lambda, we will get lambda squared. And similarly here, when you multiply this lambda by this lambda, you are going to get lambda squared. But we are going to truncate the expression to first order, because as I said, we are interested only in the first order. Okay, you can in principle do the calculation also for higher orders, and you will get more and more terms, and that will become more and more complicated. But let's continue to first order. So we will keep the terms up to first order. So this is approximately equal to, so we are going to get 1 over kh squared plus m squared. Then you get a contribution from this term multiplied by this. So let me write it. We have plus lambda over 8 summation over n1 not equal to n2, 1 over k n1 squared plus m squared times 1 over kn2 squared plus m squared, and then we multiply by 1 over kh squared plus m squared. And then we get all the other terms, so in particular this and this, they will be multiplied by 1, because if we multiply them with this term, we will get a higher order contribution. Let's see if I can copy these terms without having to rewrite them. So maybe I can save some time because these are quite long expressions. So let me go below. Here I have something like this, something like this. Here I have a plus, and then I have these terms. Now, if you check this summation here, this summation can be split in more parts. In particular, the summation is equal to summation over n1 not equal to n2, n1 equal to h, so basically you are summing just over n2 if n1 is equal to h, and this is equal to, then we have plus summation over n1 not equal to n2, where n1 is not equal to h. And then you can split them one more time, so you have summation over n1 not equal to n2, n1 equal to h, and then you have n2 not equal to h. This is just how we can rewrite this summation here. Then we have to rewrite this summation plus summation over n1 not equal to n2, n1 not equal to h. Then we can assume that n2 is equal to h in this first summation, and then we can split it like this, summation over n1 not equal to n2, n1 not equal to h, and n2 not equal to h, like this. But now you can see that due to the symmetry of the indices n1 and n2, these two summations are exactly the same. So basically, let me do it here. These two can also be written as twice summation over n1 not equal to n2, n1 equal to h, and 1, let me write it properly, equal to h, and n2 not equal to h. So basically here we are just summing over n2 because n1 is fixed and equal to h. Now you can see that when we rewrite this summation as a sum of this summation here and this summation here, you can see that this term, so let me, probably I can change color, so this term here will be cancelled by this summation here. So I can think, maybe I can thicken my pen, my red pen. This will be cancelled by this. Then you can see that this summation here can be put together with this summation here, because they are exactly the same. n1 equal to h and n2 not equal to n1 also means that n2 should not be equal to h. This is implicit, right? In order for these conditions to be satisfied. And when you set n1 equal to h in this part of this summation, this term can be put together with this. So you will get 1 over kh squared plus m squared all squared, right? So you can sum those two terms. Now, do we have any other terms to consider? Actually, I think that we are all set because all the other contributions are just 0. So here I have put a plus, but there is no plus there. You can put plus 0 if you want. This is just useless. So when you put all the terms together, Here you simply have this is equal to, we have 1 over kh squared plus m squared, and then you have plus, you have lambda over 8. Remember that we are considering just this summation, so you have 2 minus, here you have 3 times 2, so you have minus 3 times 2, and then you have the same summation over n1 not equal to n2, n1 equal to h, n1 equal to h, and n2 not equal to h. So you have 1 over k n2 squared plus m squared, 1 over kh squared plus m squared, all squared. And you can also rewrite it more properly. So here 2 minus 6 is minus 4. So what you get is 1 over kh squared plus m squared minus lambda over 2. And then this summation can be rewritten more properly because we can change the name of the variable n2 to n. So we can sum over n, and we have to make sure that n is not equal to h, because I mean it's useless to use n1 in the conditions, because we know that n1 is equal to h. So it's useless to write n1. We can write h since they are the same, and then we know that n2 should not be equal to h. So in this case we are going to write n instead of n2. So this is how we can write it: 1 over kn squared plus m squared, 1 over kh squared plus m squared squared. And this is basically the result of our calculation. Remember that this is equal to average of mod phi hat sub h squared, like this. Now, if we want to go back to the continuous domain, so if we want to go back to our continuous variables, we simply have to replace the summation with an integral. And in principle here, you have to take into account also the fact that n should not be equal to h. But when you go back to integrals to the continuous domain, the fact that you should not sum over n not equal to h is not really important, because remember that this summation should be replaced by an integral d for, let's call it q, the variable, let's call it q, divided by 2 pi to the fourth. So if you just subtract one of those values, you basically have to subtract the value multiplied by the differential. So if you think about it, when you think that the differential is something very small, that's a negligible amount. So let's rewrite the result to first order. So the result is correct to first order. We have the average of mod phi hat of k squared equal to, or approximately equal to, you have 1 over k, which in this case is a continuous variable, k squared plus m squared. So this is just a classical propagator. It would have been much simpler to just derive this part, because you can see that even just the first order is very complicated if you want to carry out the path integral. But it is just the way it is, and as soon as you want to use these formulas to calculate higher orders, you get even more complicated integrals to carry out. So you have minus lambda over 2, then you integrate d4q over 2 pi to the fourth. This is going to replace the summation. And then you have 1 over q squared plus m squared from here. And then, of course, outside of the integral, you have 1 over k squared plus m squared squared. And in principle, you also have higher order terms. Now, in the language of Feynman diagrams, this simply corresponds to a single line. So this is a propagator, where at the end of the line here you have phi and phi, right? And you have to think that these are just two different space-time points. And this is how you represent the propagator. Then you have another contribution from here. In particular, you get something similar. So you have phi here and phi here. But then you also have an internal loop. So here you have a loop. This is a vertex. And to the vertex, we associate the expression minus lambda. Then to the loop here, we associate the integral d4q over 2 pi to the fourth, 1 over q squared plus m squared. And then to these two edges, we associate 1 over k squared plus m squared. Similarly here, so you have 1 over k squared plus m squared. And here we associate, of course, 1 over k squared plus m squared. You also have a factor of 2 here in the denominator, and this is due to the symmetry factor of the graph, of the Feynman graph. And basically, you can see that you can associate Feynman graphs to the path integral. So the path integral is very useful because it gives you the intuition behind the reason why we have such Feynman rules. But anyway, you can see that to calculate path integrals gets more and more complicated as you increase the complexity of the calculation. If you have interactions and you want to calculate the path integrals by considering the interactions, that's going to be quite complicated. But once you get the hang of Feynman diagrams, this becomes easier. So without having to carry out all these complicated integrals. For example, here you can simply say that here you have, for example, momentum k. Due to the conservation of momentum here, you have to have k, and inside the loop, in principle, you can have any kind of momentum that we can call q, which is not defined according to momentum conservation, because you can see that this q exits the vertex here. In principle, it can also enter. Then it will enter the vertex here. This is to say that you can see that momentum conservation does not allow you to calculate q. So you have q plus k, which is the amount of momentum that enters this point, or if you want the loop, this is equal to q plus k, which is the amount that exits the vertex. Here you have q plus k. And since q is not defined, you have to take into the possibility the fact that q can take any value. So you have to integrate inside the loop. And this is why we have this integral here. And this is how you can think of Feynman rules, and you can define them.